Alright then everyone, welcome to part 2 of your introduction to electronics, your first steps. Okay, and we're going to continue with currents and voltages. Going to bring some new stuff, circuits, and explain a little bit more about currents and voltages, and do insulators and conductors and how you get currents out of voltages and where the sources of voltages come from, you know. So we'll still be a little bit atomy at the moment, but mainly instead of relating to atoms and things, it's mainly the electron, and we'll be using concepts like currents and voltages and you're not. And yes, I'm in the lab today on the whiteboard simply because I've been kicked out of the office having a refurb, and yeah, I'm stuck in here for a bit. So let's kick things off. Alright, and to kick things off with in this one, we're going to cover a big chunk all in one go. How to obtain a current from a voltage source, insulators and conductors, and touching on circuits. So then let's kick it off with a voltage source. Now then, that is going to be our voltage source. And the voltage source is split in half. I don't actually see that too well. Let's do that again. There we go, that's a little bit clearer. There we go, and it's split in half. Top half is positive, bottom half negative. So then, negative contains all of our electrons. Okay, this is a negatively charged. Positive contains all of our atoms, okay, with a lack of electrons. So, negative, all our electrons down here, want to migrate to the top. Now, without some sort of path, they can't do that, okay, because they haven't got they don't know where to go. They want to get there, but they haven't got a clue how. So think of it, you want to take a journey somewhere, you want to go home from to work, but you don't have a road, you don't have a path, so you can't do it. It's impossible to do, even though you do want to. So as an electronic engineer, what we need to do, we need to create a path. And in order to do that, the easiest way is this. There we go, we've created a path, or a conduit if you like, or a track, or whatever, from positive to negative. That way, all of our electrons that are stored down here flow down our track or down the path and get to the positive. That is basically current flow. So there we go, we've got a current going from negative to positive. Now, what do we use to conduct, or, you know, to allow our electrons to flow? What materials do we use? So there are two different categories. Well, there's actually three, but I'm only going to touch on two for now, because the third one's a special case. Conductors, insulators, semiconductors. Semiconductors we're going to leave out, okay, because they're a little bit funky. We need to understand how electricity works, we need to understand a couple of the components first, and we need to understand materials. So we're going to touch on that later on. Right now, conductors and insulators. Conductors are the ones that you use to create paths with. They're the materials that have lots and lots of electrons in them. You've got loads of atoms that contain loads of electrons, and they're easy to move. You can kick them out of the orbit, perfectly easily, and you can set up, this flow. So think of it as an extension of your negative side. So what we've got is loads of atoms with electrons, and we've got absolutely shitloads of them. All in this conductor. And what happens is the electrons that are in this atom here get attracted to the positive. This one now becomes positively charged because it's got a lack of electrons now. The atom next to it has got shitloads again of electrons, so it migrates to this one. And this one again migrates to this one, to that one, to that one, to that one, and you get this pass-to-parcel effect taking place until you get all the way back to here. This one's got a lack of electrons now, and from the negative side it drops in, and eventually this one will migrate its way all the way around to the positive. And there we have it. We have this pass-to-parcel effect of electrons jumping from atom to atom in a conductor, going from negative to positive. That's what conductors are, okay? The materials which allow electrons to flow. On the other hand, insulators, they're the opposite of conductors. They block the flow of current. So if this was an insulator, all of these atoms with their electrons, the electrons will be very tightly bound to them. There won't be many of them, okay, so they're it's a balanced atom. There's as many electrons as there are protons, and they're very tightly bound, and the attraction doesn't happen, and you don't get any current flow or anything like that. Nothing happens. So it's a block. You could think of it as for electricity. Electricity doesn't flow. It would be as if it's not connected at all. That's what insulators are. Conductors, insulators, some examples. What I've got here, insulators, anything. Plastic, got some plastic goggles here. That's one thing. Got some rubber tubing. Wood. It's a bit of a funky one. It's in between the two. Okay. Something like trees and things like that. Any wood that's very, very moist, very new wood, can be a little bit conductive. Old wood like this, okay, it's dried out a bit, less conductive. All your conductors, things like this piece of metal, all metals are generally conductors of electricity. Very good. Anything that isn't a metal generally is an insulator. Just an example, wire, the key essential thing that we do use everywhere in electronics, okay, is, there we go, copper conductor, okay, so that's a copper wire in the centre with a rubber insulator on the outside, so we can hold the wire without shocking ourselves. So exterior doesn't conduct electricity, so we can hold the cable while our current travels down the centre, our conductor. Another example, okay, circuit boards. On that side you can see the copper, and that side is our insulator, so so you can see our copper tracks up and down here. That's what carries our current. They're all separated. Okay, you can see, yeah, you can see them up here. So you've got one copper one, another one, and another one, all on here. So yeah, that's another example of a conductor. And on that side, this is the plain side, our insulator. So there we have it. Some examples. Other insulators that are out there, you've got glass, you've got ceramics, plastic, rubber, you know, wood in general is an insulator, although there are some exceptions. Conductors, normally metals, you can get some conductive liquids. Right, but predominantly this is what we use, and this is sort of stuff that you make your circuits with, or circuit board and stuff. There are other mediums which you can use. You can use conductive ink, so you can paint on, or draw on conductive tracks, things like that, or conductive paths. Graphite is one as well. The graphene, the stuff that's in a pencil, okay, a leaded pencil, you can use that as a conductor. And, yeah, right, moving on. So, conductors, insulators covered. How current gets from the negative to the positive, and that setup there is the most basic circuit. So the circuit is, it's a connection from the negative to the positive, and that's your first circuit. That's the most basic circuit you can get, and we've got something happening. We've got our voltage, which is our force pushing around our electrons, and the electrons is, current. So then, I'm going to turn that on top of its head now. Back to this. We've got our circuit, or our track, and whatever connecting the two. And I've been saying that current flows from negative to positive. That is 100% correct, and it's also 100% wrong. Because in electronics, since the beginning of electronic engineering, where our fathers of electronics, our granddads of electronics were working, they thought, yeah, we've got our voltage source and what have you, we've got something physical there, we've got something positive. Well, we've got a positive voltage source, we must have a positive current, and positives, flow from positives down to negatives. We can't get, current surely can't be a negative, otherwise it's an absence of current or an absence of power, and that just doesn't make sense. So since the beginning, we've always assumed it goes opposite way, and that's stuck. So where I've been saying that current flows from negative to positive, if you look through any textbook or anything, we'll always assume that it goes from positive to negative, and that's how we're going to work it from now on, unless it's a negative going current, and I'll come on to negative voltages and negative currents later on. We're just dealing with the positives, baby steps. Right then. So that's what we do now. Current flows from positive to negative, even though it actually flows in the opposite direction. This is just to confuse the matter, okay? Turns a very easy subject into something confusing, and that's why we get paid loads, because we've done it that way. Alright then. That's current sorted out and everything. Insulators, conductors and circuits. Next up, voltages. Where do we get our voltages from? What exactly is this big blob? Well, voltages come in two categories, primary and secondary. I'm going to tackle secondary first, because that's basically what this is. This is a secondary power source. Secondary power sources is a stored power. It's generally, created chemically. So we're looking at things like these things, batteries. Okay, we've got our lead acid. Okay, as you can see, red, black, as in red and black, positive, negative. And PP3 batteries, positives and negatives, and it's written on the side, positive and negative there, you can see that, and AA battery. All secondary sources of voltage, secondary voltage sources are predominantly storage devices, okay? They contain a set amount of voltage. So if this was 9 volts, which it is, okay, it contains 9 volts of power, essentially. So this would be 9 volts. Simples. The other group of what voltage comes under is primary. So secondary. Primary is slightly different. Primary source of voltage is a voltage that's always there. Unlike this, that can run out of power, okay, as it's plugged in, it gets used up. Once it's used up, something like this, you throw it away and you buy a new one. primary sources don't run out of power. That's the sort of thing that you get from the grid. Okay, your mains that supply the stuff that comes out of the plug socket. So here in the UK, 240 volts RMS comes out of that plug socket, and it's guaranteed to be there 24/7, 365 days of the year. You know, it's continuously there, and as much as you draw out, you've got it being pumped back in, so you never actually lose it. That's what primary source is. And that's secondary and primary. Those sources are now split down into another two categories, AC and DC voltages. So let's write this out. Oh, it's a long haul today. So then, well, I've been about a half hour so far. We'll do this on a quick. Right then, DC first up. DC volts. What I mean by DC volts is stuff that you get out of the battery. If this is, what's this, 6 volt battery, okay, it says it up here, 6 volts. This is a constant value of 6 volts. So if we draw a graph of this, so that's the D up there, that's 6 volts, 6 volts is here. That value is a constant value and it doesn't move, and it's fixed. It's nowhere here, it's nowhere up here, it's there, it doesn't shift, and it is a continuous 6 volts. So in time, as we've been saying this has been 6 volts dot, continuously 6 volts, join the dots. What have we got? We've got a straight line. That's how we denote a DC voltage. Just to say it out, DC voltages, the symbol for it is this. It's a flat line with a dotted line underneath. That's what the symbol for a DC voltage. Here is what we go for it, or it can be written VDC if you need. And that is a DC voltage. It's a constant value over time. This is primary source, that'll be a constant value. Secondary, okay, this does diminish over time, okay, as you use up that power, the voltage does drop accordingly. Now then, next one up is slightly different. Before I do that one, next one, should say if you've got DC voltage, when you draw a current from a DC voltage, you get DC current as well. Same thing applies. Next up, AC voltages and AC currents. So, AC voltage. Okay. Right, so this is our graph this time for it. AC voltages are slightly different. It's what's known as an alternating voltage, okay, or an alternating current if we're getting in currents. It varies between two values of a constant value. Yeah, it's confusing. It's a constant value, but it's a fixed value. Let's say take our, let's say 12 volts this time. 12 volts AC, now it can be represented in lots of different ways, in amplitude and peak to peaks and in RMS, and we'll go through that now, but just say it's alternating voltage, alternates between two values, say plus 6 and minus 6. So we've got our dot up here and we've got our dot down here. Okay, it alternates between those two values, but then it's a fixed amount that it alternates between. So from plus 6 to say minus 6 in this case, and that dot in that dot goes up and down, up and down, up and down continuously. that was in time, it would look something like this. That's what it looks like. You may recognise that. It's a sinusoidal waveform, okay? That one in particular, a sine wave, but generally it's sinusoidal, I like to call it, because it's, it can be a little bit, it can be shifted backwards and forwards, so it might start up here, it might start there, it might start down here, it could start, smack bang in the middle. Who knows? That's what we mean by alternating, okay? It's continuously fluctuating between two different values and all the values in between. So it passes through all the values up to 6 volts, and all the values down to minus 6 volts, all the values back up to 6 volts, all the values down to minus 6 volts continuously. This swing is happening all the time. That's what AC is. It's a swinging voltage. Now, as I said, this can be represented in lots of different ways. The first one, the most easiest one, the most common one, is peak to peak. From peak to peak, okay, this voltage will be 12 volts. Why? Because it goes positive 6, negative 6. So 6 to 0, 6 to 0, 6 plus 6 is 12. From one peak to 0, from 0 to the next peak, it's 12 volts. That's what we mean by peak to peak. And it's represented as normally as a V. P. 12 peak to peak. Next one up is the amplitude. The amplitude is referred as basically it's the positive swing from 0 to plus 6 volts. So if we're dealing with amplitudes, okay, so this will be normally just V amplitude. This will be 6 volts from 0 to 6. The other one is RMS, which is a special case. That's if you want to try and compare AC to DC. RMS is a bit like the average of this waveform, and it's sort of like the amount of power that the AC generates compared to the DC equivalent. So it's sort of like if you're trying to work things out in terms of DC, because DC is a lot easier to work out things because it's a constant value, we generally use RMS. So volts RMS. And that's normally the root mean squared of the value. So, root 2 of the amplitude is our RMS value. So this would come out to probably about 4 volts RMS, around that sort of figure. But we'll get onto that in the future. Suffice to say, DC is a fixed voltage, it's a straight line. AC, it's a swinging line. Whenever you see this symbol associated with a power supply, it's generally going to give you AC. You can see the flat line with a dotted line underneath associated with a power supply is generally going to be a DC voltage. All voltages have a plus and minus, whether they're AC or DC. Doesn't matter in the slightest. And yeah, and that's really all I'm gonna say for this one. It's been going on for quite some time now. What is it? No, I didn't go on for. I've only been going on for 20 minutes. Well, let's go on a little bit more. Right then, reason why you're well, this is DC. And it remains DC because it's a chemical reaction. That chemical reaction is a linear process, it's a straight process. So as you draw that current, you get that straight line, and it continuously does it, and it's continuously, it's a linear process. That's why it's straight. I'm not going to get into the chemically stuff because I'm not a chemical engineer. And the other stuff, the primary side of voltage sources, it's generated normally electromechanically, or electromagnetically, I should say. That's why you get variations. Now, I suppose we start from the beginning. All your because we're talking about grid and we're talking about electricity, all of the stuff that comes out of your plug sockets is predominantly going to be generated from powerhouses that burn fossil fuels or nuclear, or going to be, you know, some sort of renewable energy source. All those sources are all based on alternating voltages. That's why you get alternating voltage out of your plug socket. Not only that, alternating voltages are a lot easier to transmit long distances. So it's a bit like a win-win-win-win situation, but we end up with that alternating that we convert into a DC later on. Anyways, how do we generate the AC? Why is it different? Well, like I said, it's generated in your fossil burning or your renewables houses, and the way how it does it is this: burn your fuels, you get heat. Heat heats water. The heated water turns into steam, and you use your steam power to drive something mechanical, normally a turbine or a fan or something, you know. As you pump this steam through the system, you can spin a turbine, or spin a turbine connected to a shaft, so you've got a rotating shaft. This rotating shaft, this is your... Can you see that clearly? Yeah, just about. You've got your rotating shaft. On our rotating shaft, we've got, you know, loads of a conductive material, normally copper, a copper wire or something. And that copper wire is spooled around our spinning shaft. So we've got our wire around our shaft that spins round constantly, and that spins in a magnetic field. So we've got our magnetic field, which is north and south. Okay, so we've got north and south poles. As this conductor spins through the magnetic field, the field is so strong it dislodges your electrons, and hence you get current flow. Trouble is, you've got north and south, and this spins. So 1 minute it's your electrons are being flung in one direction because it's going north to south, and the next minute it's in a different direction, it's spun round, you know, 180 degrees, it's now south to north, which means the electrons get fired in the other direction. So you end up getting, you know, a sort of backwards and forwards motion. And as you can see, that's turning into a sinusoidal sort of shape. That's why you get an AC coming out of your plug socket, because it's how it's generated. Now, I did mention renewables, wind power, wave power, you know, hydro power. Basically, all that stuff is all converted into rotational motion, and you get that same sort of effect. Exactly the same thing. Solar, on the other hand, it's not based on magnetics, but you get the same principle, because solar, if this is time, that's volts, over the course of 24 hours, you've got night, day, and then night again, you get this sinusoidal shape over and over again. So it's a very common process. That's why you've got a lot of sinusoidal signals, and that's predominantly why it comes out of your plug sockets, and that's your primary source. DC, on the other hand, it's a chemical reaction between various different chemicals, various different materials, like you know, you've got your alkali batteries, you've got your lead acid batteries, you've got zinc fluoride and what have you. All different materials, all different chemical amounts, and yeah, that reaction is a linear reaction. It's what's reasonably linear, which is why you get that constant voltage, but it does deplete in time. So I'm going to leave you there. Next time we come into this, we're going to be dealing with power sources instead of blobs on the whiteboard, and instead of, you know, insulators or conductors, we're going to be dealing with wires and whatnot, and we'll start to look at building circuits, series, parallel, and we'll do that with light bulbs next, just to get you an idea of how to power a system, just with basic turning on a light. So, see you next time.